Hello and welcome to the review for the final. Ms. Morgan and I have selected these 8 problems to jumpstart your studying for the final. They are a nice cross-section of the material we've covered this semester. Cover the bulk of the stuff we covered on the first 2 exams, but it's assuming that the sequence and the series stuff and most of the vector stuff is more recent and more fresh in your mind. So we are concentrating on the earlier material. This is a jumping off spot, not to be thought of as inclusive, fully covering all the material for the final. It's just to remind you of things you haven't seen in a while. And so with that in mind, let's jump right into this first problem. Trig substitution. It's been a while. We did this back in January. And this is for evaluating integrals which involve the sum or difference of squares. And so when I look at this problem, I see, oh, the 9 minus x squared is the difference of squares. And so first thing I want to do is choose my substitution. And the way I'm going to choose that substitution is I'm going to draw a triangle. I'm going to draw a right triangle. And I want 9 minus x squared to be involved in one of the sides of that. And I know that the hypotenuse loves positive things. This is a difference of squares, so I know the 9 minus x squared has to be one of the sides. I also know from experience from Pythagorean theorem that it's got to be square root of 9 minus x squared. Now, when I'm looking for the hypotenuse in the other leg, I remember the hypotenuse loves positive things, so the hypotenuse is going to be the square root of 9, which I can also just write as 3. And the other leg is going to be the square root of x squared, which is going to be x. Now, the simplest fraction I can make is x over 3. Right? I don't want to involve the ugly square root, so I'm just going to involve the x and the 3. And I want to be able to solve for x, so I want to put x in the numerator. I look at that and I say, oh, well, that's a leg over a hypotenuse. And I say, oh, the trig functions that could be are sine or cosine. And we prefer to avoid the cofunctions because their derivatives involve an extra minus sign that we'd like to avoid. So I'm going to make that sine of theta, which means that x is not only a leg, it's the opposite leg. So it's the theta is in this corner here. Next thing we want to do is we want to be able to substitute. And so we need to be able to replace x's. And so x equals 3 sine theta. And we need to be able to replace the differential. So dx equals 3 cosine theta d theta. And lastly, looking at the triangle, I can see that 9 minus x squared over 3 equals adjacent leg over hypotenuse is cosine theta. And so I can say that the square root of 9 minus x squared equals 3 cosine theta. We're almost ready to replace everything in our integral, right? We have the x's, which will help us replace that. We have the dx, we'll replace the dx. Then we have the 9 minus x squared square rooted, which will help us replace the denominator. What we have not figured out yet is what to do with these bounds. So don't forget to change your bounds. X equals 0. We'll go to 0 over 3 equals sine theta, which tells me theta equals arcsine of 0, which is 0. And x equals 3/2. We'll go to 3/2 divided by 3 equals 1/2 equals sine theta. I know that sine theta is 1/2 when theta is pi 6. So now I'm ready to replace everything. My new integral is going to be from 0 to pi 6. The numerator, x squared is 3 sine theta squared. Cosine is 3 cosine theta d theta. And the denominator is the square root of 9 minus x squared, which is 3 cosine theta, all raised to the 5th power. Let's bring our coefficients out in front. I have a 3 squared times a 3 divided by a 3 to the 5th. Integral from 0 to pi 6 sine squared theta cosine theta over cosine to the 5th theta d theta. The 3's in front reduce significantly. It becomes 1 over 3 squared, which is 9. Cosine cancels. So I get sine squared over cosine to the 4th theta d theta. And when I look at that, I say, ooh, I don't know how to do that in the sines and cosines. Maybe some half-angle formulas could possibly help, but I don't want to go down that route right away. And when I'm stuck with sines and cosines, I think, okay, what other trig functions go well together? Maybe secants and tangents. And so I look at that and I say, oh, maybe if I write that in terms with secants and tangents, it'll be a little bit nicer. And so I say, oh, sine squared over cosine squared theta, 1 over cosine squared theta d theta will help me rewrite this in terms of secants and tangents. Sine squared over cosine squared is tangent squared theta. 1 over cosine squared is secant squared theta d theta. And now that is much nicer because I can see, oh, secant squared is the derivative of tangent, and so u equals tangent will help me out quite a bit. U equals tangent, du equals secant squared theta d theta, x equals 0, u becomes tangent of 0 is 0, x equals pi 6, u becomes tangent of pi 6, which is 1 over square root 3. And so I get the integral from 0 to 1 over square root 3 of u squared du. And so the integral that started out ridiculously ugly at the start becomes ridiculously easy at the end, because now we can just use the power rule. Raise it by a power, divide by that new power, and then plug in our bounds. We could simplify that a little bit more, but that is sufficient for now. I will see you in video 3.